Hi everybody. Today's lesson is going to be on section 7.4, Integration of Rational Functions using partial fractions. Okay, so what are rational functions? They're just fractions, okay? So what we're saying is, let's suppose we have a fraction of polynomials. This technique is going to help us, okay? So I want you guys to notice something. Notice that if I were to ask you guys to integrate, for example, 4 over x minus 4 plus 3 over x minus 5, this would not be a difficult integral to do, right? Because we know we have the linear substitution shortcut. And so each of these, because they're linear and the slope is 1, you just end up having the natural log of x minus 4 plus 3 times the natural log of x minus 5, right? Okay, so the integral is not difficult. Of course, we still have a plus c. Let me not forget that. But what if somebody were to give you this problem, right? What if somebody were to say, let's add these fractions together first to try to make your life more difficult. So let's suppose we were to add 4 over x minus 4 plus 3 over x minus 5. How would you add these? Well, we know using common denominators here, if I multiply that by x minus 5, and if I multiply this guy by x minus 4, we actually end up with 4x minus 20 plus 3x minus 12 over x minus 4 times x minus 5. And this would actually give us 7x minus 32 over x squared minus 9x plus 20. Now notice this and this are exactly the same thing, right? All we did is used algebra, except if I were to give you this integral instead, and we hadn't done that part from before first, this would be a lot more difficult, wouldn't it? So we do not know what to do when we look at something like this, even though we know that this actually just becomes that answer, right? Because this is exactly the same thing as what we started with algebraically. Okay? So, integrating the same expression is difficult when it is combined into one fraction. Okay? So, we need a way to break these things apart. We know how to put together two fractions and add them and get a more complicated fraction, but how do we go the opposite? How do we take 7x minus 32 over x squared minus 9x plus 20 and write it as 4 over x minus 4 plus 3 over x minus 5? This has a name. So we have something called partial fraction decomposition. So partial fraction decomposition PFD is what I refer to it for short, okay? So partial fraction decomposition is the process of writing a rational function as a sum of simpler rational functions. Okay, so this is going to be our method. This is going to be our approach, I should say. What we want to do is we want to take something that looks complicated and split it up and write it in as easy a form as possible, because it is easier to integrate the sum of lots of simple things rather than one complicated thing. So what are the steps? So let's go through these one by one. So step 1, we call this setting up the PFD. So what are the steps for setting up the PFD? Okay, so step 1, or I shouldn't say step, I've already called step 1. Okay, so the first thing you have to do is if the degree of the numerator is greater than or equal to the degree of the denominator, use long division to, you know what, let me give this another name. Instead of calling it setting up the PFD, let me call this step 1 long division, okay? If the degree of the numerator is greater than or equal to the degree of the denominator, use long division to rewrite as follows. So if you start off with something like f of x divided by g of x, you can rewrite this as whatever the quotient is plus, and then the remainder divided by whatever the old thing was on the bottom. Let me actually write it as a g of x here, just so it matches what we started with. And so the whole point of using long division to write it this way is that this guy now, the degree of r of x is smaller than the degree of g of x. And now, do the following steps with r of x over g of x. In other words, we're going to, instead of doing the problem on the f of x over the g of x part, we have done this because now we only need to do partial fractions on this second fraction. We don't need to do it on the first anymore because we were able to rewrite it. Okay, so that's if the degree, okay? Otherwise, we can just skip to step 2. Step 2 is where the actual setup begins, okay? So step 2. So we are going to assume first that we have linear factors in the denominator. So what do you do for these factors? So linear factors in the denominator. So if you have linear factors in the denominator, that means that your fraction looks something like this. You have p of x over some linear factor, let's call it ax plus b, and it's to the nth power. So this is called, by the way, this one we're going to call setting up the PFD. Okay. So the way that you set it up is as follows, okay? You create an unknown and you divide it by the linear factor, and then you create another unknown and you put it over the linear factor squared, and you keep doing this pattern going up by one power at a time until you get to the very last one, which is going to be an over ax plus b to the nth power. Okay. So this is what it looks like when you have linear factors. So what happens now if instead you have irreducible quadratic factors? In the denominator. Irreducible just means that you can't factor it, okay? And there's lots of polynomials that are quadratic that you cannot factor. So what do? So these are going to look like this, right? We have something like p of x over ax squared plus bx plus c, right? So here's how this works. What you're going to do is you're going to break this up into n pieces again, except each piece has two unknowns. First, you're going to have a1 times x plus b1 over that thing. And so you have two unknowns there. And then you have a2x plus b2 over... Oh, I forgot to mention that this is to the nth power. I apologize. So that's going to be squared, and you do it for each power until you have the very last one. You do it n times. Okay, so that's what it looks like. So notice that for this, you have n unknowns, right? Your a1 through an are your unknowns. And for these, you actually have 2n unknowns, right? Because each of these has a pair of unknowns. a1 through an and also b1 through bn are all unknowns. So we do the above for every distinct factor in the denominator after factoring it. So in other words, factor the denominator, and then you do what the steps that I just wrote down, you do that for every factor, and then you add it all together. Okay. So that's it. That's it for step 2. But I want to practice, because these first 2 steps are already a little bit complicated, so I want to practice doing just those 2. So let's practice. Just steps 1 and 2 of partial fraction decomposition. So in other words, we just want to set up. So set up the following. PFDs. Starting with number 1. What What if we have x cubed plus x over x minus 1? So step 1 says that if the degree of the top is greater or equal than the degree of the bottom, we use long division, right? So let me just say that the degree of the top is greater than or equal to the degree of the bottom. And so this means we use long division. So let's see what we get. Let me remind you guys of how long division works, okay? So we have x cubed plus, I'm going to have to insert some placeholder terms. And we're going to divide that by x minus 1. So the first thing we ask is x times what gives us x cubed? And the answer is x squared, right? So if you multiply x squared times x minus 1, you get x cubed minus x squared, except we're going to subtract this, right? Because that's what you do in division, right? So if you subtract this, just remember that these signs change inside. And so you're going to end up with x squared, and then you drop these, and you do it again. So now let's do it one more time. Or actually, we're going to have to do it 2 more times here. X times what gives us x squared? We have x, right? Positive x. So we have plus x. X times x is x squared. X times negative 1 is negative 1x. But we subtract. Once we subtract those, you actually end up changing those signs again, and we're left with 2x plus 0. And our last one here, x times what gives us 2x? It's actually positive 2. And then multiply that out, we get 2x minus 2. Subtract. So that becomes a minus and a plus. And then we end up with 2. So our remainder is 2. And so here's how we write our answer. Our answer is x squared plus x plus 2 plus, and then the remainder over x minus 1. We cannot go further because for step 2, in this last one here, right, we can only proceed if we actually have more than one factor in the denominator. So remember, we are always beginning. I wrote that here after factoring, right? You got to factor the denominator first. If the denominator doesn't factor, you cannot use PFD. Okay, so we're done. That's it for this problem. Okay. All right, so let's go with number 2. We're going to set up the following. X squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Okay, so step 1 is to look at the top and the bottom and see if the degree of the top is at least equal to the degree of the bottom, and it is not. So we can go to step 2 now. We need to factor the denominator. So let's factor 2x cubed plus 3x squared minus 2x. So the first thing I can do is I can pull out an x, right? If I pull out an x, I get 2x squared plus 3x minus 2. From here, I need to factor this, right? I can see if this thing can be factored, right? So if it can be factored, I need to have a 2x and an x there. So let's see. Maybe -1 and +2 works, right? I believe that's it. Yes. So there's our factorization. Okay? So this is what we have. Bottom becomes x times 2x minus 1 times x plus 2. And so what's the partial fraction decomposition going to be? Remember, we have an unknown plus another unknown plus a third unknown. Now, why do I only have one for each? It's because each of these was to the first power, right? These are all to the first power, so I only needed one of them. And remember what I said in my setup, we're going to add the results together, right? Then add it all together. Okay? So that's our setup. Okay, let's try another setup. We have x to the 4th minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1. And look carefully, the degree of the top is 4, which is greater than or equal to 3, which is the degree of the bottom. Okay, so that means we can go ahead and use long division here, right? So let's do x to the 4th minus, well, let me do it this way. X to the 4th plus 0x cubed minus 2x squared plus 4x plus 1. And we're going to divide that by, I did not leave enough room. I apologize. Let's try this one more time. We have x to the 4th plus 0x cubed minus 2x squared plus 4x plus 1. And we're dividing by x cubed minus x squared minus x plus 1. There we go. So now let's do each one at a time. X cubed goes into x to the 4th x times, right? And if you multiply that out, you get x to the 4th minus x cubed minus x squared and then plus x. And we're going to subtract all of these. That means we need to change all of the signs, plus, plus, and a minus, right? And so what do we end up with here? We get x cubed minus x squared plus 3x plus 1. And x cubed times what gives us x cubed? It's going to be positive 1. And then multiply it by 1. So we have x cubed minus x squared minus x plus 1. And we're going to subtract this. So we change all of these signs. We end up with, so actually in this one, that's gone and that's gone. So we have 4x. Actually, we just get 4x, don't we? So then this is equal to x plus 1 plus the remainder is 4x and the denominator stays the same. Okay, we're not done here, okay, because we need to now move on to step 2, which is to deal with this fraction, and we're going to factor that denominator. How do we factor something that has 4 terms? So x cubed, so we have 1 minus minus 1. So how do we factor this? We're going to use a method called factoring by grouping. Whenever you have 4 terms, it's worth trying this. We have x cubed minus x squared, and then on this one we have negative x plus 1. So in the first group, we can pull out an x squared, and then we have left x minus 1. And in the second group, we can take out a negative 1, and then we have left x minus 1 again. And because these are the same thing, we could pull out the x minus 1, and we're left with x squared minus 1. But we're not done yet because this is a difference of squares. So x squared minus 1 factors into x minus 1 times x plus 1. And we still have an x minus 1 from before, so this means that my final factorization looks like this. Okay. So I had this before, so let me now write down what I have, okay? I have 4x over, my bottom is now x minus 1 squared times x plus 1. So what's my partial fraction decomposition going to look like? Remember, you need an unknown for each of the powers that you see. So because we see a second power on the bottom for that one, it's going to look like this. A over x minus 1 plus b over x minus 1 squared, and then plus c over x plus 1. Okay. Don't forget that we had this x plus 1 over here. I don't want us to forget about that. It's easy to forget when you go ahead and do other stuff. So I'm going to write plus x plus 1 also. You know, x plus 1 plus. So if we were integrating this in the end, we would not be able to forget about that x plus 1. Okay, let's keep going here. Let's do a few more. So this is going to be number 4. We're doing 2x squared minus x plus 4. And the bottom is x cubed plus 4x. Notice that the degree of the top is smaller than the degree of the bottom, so we have no long division to do. Let me just write it this way, no long division. And so I'm going to factor the denominator. So let's write down x cubed plus 4x here. We're going to factor it. And all I see is we can pull out an x. Now be careful, even though we might be tempted to factor x squared plus 4, there is no formula that allows us to factor a sum of 2 squares, right? Hopefully you guys remember that from algebra. So this means that we have 2x squared minus x plus 4, and the factored denominator is x times x squared plus 4. So how do we set up a partial fraction decomposition for this? Remember, we need an unknown for that guy, and each of these is to the first power again, so we're only going to need one more fraction here, except I need to create a pair of unknowns, right? Because it's a full linear term. Again, guys, this right here, we call this an irreducible quadratic, right? You cannot factor this quadratic. Okay, let's keep going. I want 2 more examples here that are going to illustrate this. Let's look at number 5. We have 4x squared minus 3x plus 2 over 4x squared minus 4x minus 3. So the degree of the top is equal to the degree of the bottom, so we are going to use long division first, okay? So let's do that. What is 4x squared minus 3x plus 2 divided by 4x squared minus 4x minus 3. So let's see what we get. First we need to multiply by 1, and we just get itself again. And then we're going to subtract it. So this actually allows us to change the signs here, and then let's see what we get. We get x plus 5. So we have 1 plus, and then the remainder is x plus 5 over 4x squared minus 4x minus 3. Now we need to see if we can factor this guy, right? We need to factor that guy. 4x squared minus 4x minus 3. So 4x squared minus 4x minus 3. So we have a lot of possibilities here. We can maybe try 2x, 2x. Let's see, I think that's going to work, right? Plus 3 minus 1. Let me see if that works. I think I got the signs reversed there. Let me see, minus 3 and then plus 1. I think that works. 4x squared minus 6x minus, minus 4x minus 3. Cool. So then this is equal to x plus 5 over 2x minus 3 times 2x plus 1. And so my PFD on that is going to be, you just need, those are both linear and they're to the power of 1. So we have over 2x plus 1. Sorry, I don't know why I used a C. Usually we just use the letters as they come in order. Okay, so we have 2 unknowns for that one. Let's not forget too that we also had on the other page, we had this 1, right? We can't forget about that. In the very end of the problem, we would have, plus 1. The very end, okay? Okay. This will be a great example. The one I'm about to do is really going to allow us to see if we understand how all these setups work. Okay, so this is number 6. We're going to have x cubed plus x squared plus 1 over. This time it's completely going to be factored for us. Remember, we're just setting up the PFD here, and of course, the degree of the top is 3, and the degree of the bottom is much more than 3. So we cannot do any long division here. Let me just say no long division. So what I need to do is deal with these factors one at a time. So let me start with a over x. Now, the second term, x minus 1 cubed, is linear, right? But it's to the third power. That means I'm going to do it 3 times. So b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. Okay, so I did all of those. Now I'm at the next one, which is x squared plus x plus 1, and that is an irreducible quadratic. Okay, both of these are actually irreducible quadratics. So you cannot factor those. So next one now, remember we need 2 unknowns, and it's to the first power. So we don't have to do it multiple times for the same one. We just have ex plus f over x squared plus x plus 1. And now the last one's going to be the trickiest one, right? We have a quadratic, an irreducible quadratic, but it's cubed, which actually means we're going to have to do it 3 times. And not only that, but it's going to be 3 pairs. Going to run out of letters in the alphabet here. Here we go. So this would be our setup. Now, if that one made sense to you, then that means you are totally okay on steps 1 and 2 of the partial fraction decomposition. Okay. So let's learn now step 3. So step 3. Solving for the unknowns. So we've had a lot of practice setting these up, and now we need to actually figure out what those unknowns are. So here's how it works. I'm going to write out the steps one at a time, sort of the sub-steps here. So the first thing you're going to do is you're going to multiply by the LCD to clear all fractions. The next thing you're going to do, and again, I'm going to illustrate this right after, but I do want to first write out these steps, and then I promise I will illustrate these with many examples, okay? So part B, this is an identity, not an equation. So I'll explain what that means later, but what I want you guys to do is for each power of x, create an equation by equating the coefficient on the left with the coefficient on the right. Okay, and so because you're creating an equation out of each one of these with all the unknowns, I will say this yields a system of linear equations. Okay, so you can guess what comes next. Part C is going to say solve the system. Remember, we learn methods of solving systems, right? You learn some methods in algebra, substitution or elimination, or some combination of those two things. Okay? So these are the steps for partial fraction decomposition. One thing I want to say is there is a shortcut here, okay, sort of a trick. So let me just say shortcut / trick. After clearing fractions, we can plug in convenient values of x to sometimes give us solutions right away. And I will use this shortcut quite a bit, but there are going to be times where you cannot use it, okay? But we use it, so use it as much as possible. Let me just say use as much as the problem allows. And you're going to see what I mean. There are going to be times where you are not able to use it. So I will say when using PFD to do an integral, of course the last step is to integrate, right? Integrate after finishing the PFD method. So once you split it up, you integrate. So we're going to practice doing the whole thing from the beginning now with several examples, okay? So this, I believe, is number 7, except this time we're finally going to get to solve integrals. So let's integrate the following. Y over y plus 4 times 2y minus 1 dy. Okay, so I'm going to do PFD. So remember, we start off with y over y plus 4 times 2y minus 1. Again, the reason I'm doing this, and let me back up for a second here because I kind of rushed into this. The reason we're doing this is because we look at this integral and actually there is no way to solve it, right? We can't use any of the previous tricks that we know. Okay, so we're going to use partial fractions to try to break this up into 2 simpler pieces. So we're going to write it like this. A over y plus 4 plus b over 2y minus 1. Now, the next thing we do, remember the sub-steps here. First, we need to multiply both sides by the LCD to clear out the fractions. So what's the LCD here? The LCD is going to be y plus 4 times 2y minus 1. So if you multiply that, you end up with y equals, and then you have a times 2y minus 1 plus b times y plus 4. Okay, now there are 2 ways of doing this. I want to show you guys the long way and then I'll show you guys the shortcut just so that you see them both ways for this very first problem and you can appreciate the shortcut a little bit more. So first, we're going to do it the long way. Let me rewrite it here. So y equals a times 2y minus 1 plus b times y plus 4. So first we're going to use no shortcut, right? So the right side actually becomes the following, right? We have 2ay minus a plus by plus 4b. All that's equal to y. And here's how it works, okay? We're going to take every coefficient. Let me write it this way just so you see it. What we're trying to do, see, this is the whole point here is that this is an identity. This is not an equation. So in other words, this is true for all values of y. All values of y. In other words, the left and the right must be identical. So here's what we did. What I did was I took the like terms, right? That's a like term with that. And I combined them together and factored the y out. So that's what we have here. And then this guy and this guy I group together over here. Why am I doing that? Because now I can equate coefficients from the left with coefficients on the right. So look, if that's a 1 next to the y, then that means that that 1 has to match this 2a plus b right here. So 2a plus b is equal to 1. And if that's a 0 on the left, right, there is no constant. That means that negative a plus 4b is equal to 0. We have a couple of ways of doing this. We can use substitution or elimination to solve this, but this right here is a 2 by 2 system, right? So we can solve this. So what I'm going to do is I'm going to multiply equation 2 by 2, and then I plan to add the equations together after, okay? So here's my new equations now. So if I add these two equations together, I get 9b equals 1, which means that b is equal to 1/9. Okay. All right. So we get b equals 1/9 from that. And so now what we're going to do is figure out the other variable, right? So if b is equal to 1/9, that means if we use this top equation, we end up with actually, yeah, that's fine. We can do that. We get 2a plus 1/9 equals 1, or 2a is equal to 8/9, or a is equal to 4/9. Okay, so there you go. We were able to find A and we were able to find B. Now again, all of this that we just did is using no shortcut, right? No shortcut. Now let me do this on the next page with the shortcut, and you're going to see how much faster it is. So the shortcut. Let me rewrite exactly what I had. I had y equals a times 2y minus 1 plus, and then I had b times y plus 4. So we can plug in anything we want for y. That's what the shortcut says. And again, this is an identity. So what we're going to do is we're going to plug in values that cancel out one of the variables. So I'll give you an example. If I see a y plus 4 on the right, if I want to get rid of that term entirely, I can just let y equal negative 4. If I let y equal negative 4, then on the left I get negative 4. And on the right, I get a times, if I plug in negative 4, I get negative 9. Or a is equal to 4/9. Look at how quick we found that answer, right? And now, what else do I need to plug in? What can get rid of the left term? If you set 2y minus 1 equal to 0, y is equal to a half would get rid of it, right? So if you plug in y equals a half, you end up with 1/2 is equal to, on the right, you have b times 1/2 plus 4. That's 9/2, right? And so if I multiply this equation by 2/9, we end up with b is equal to 1/9. You notice that we got the exact same two answers that we got on the last page, except we didn't even need to solve a system. All we had to do was plug numbers in and solve for those unknowns. So it was much, much easier. Either way, the point is we have to get A and B. So A is 4/9, B is 1/9. Okay, what do we do now? Come back to here. That means that this integral that we're trying to solve is really the integral of, let's look at it. It was 4/9 4/9 over y plus 4 plus, and then the other one was 1/9 over 2y minus 1. So how do we integrate that? Again, these are just linear pieces on the bottom, and so we can use our linear substitution trick. This is going to give us 4/9 the natural log of y plus 4 plus, now what's this next one going to be? It's 1/9, but then we have to divide by the slope, which is 2 at the bottom, so it becomes 1/18 times the natural log of 2y minus 1, and then plus c. Pretty neat, right? It's worth pointing out, by the way, that the calculus took 5 seconds. So what took a long time in this problem is not the calculus, but the algebra. Trying to get this guy and split it up into PFD, right? Partial fraction decomposition. So getting from here to here, that's where the real work was, right? Okay, let's keep going. We're going to try a couple more examples here. So next example, number 8. And by the way, now that I've demonstrated the long way and the short way, I'm going to be using the shortcut wherever I can. But I'll also show you guys where the shortcut doesn't always work. Or it can work for a little bit, but then you sometimes have to set up at least some system to keep going. So all right, let's look at this one. Okay, so looking at this integral, let me not jump the gun this time. We don't see any u sub that we can do. We don't see a trig sub. We don't really see anything that we can do to make this problem any easier, so we have to use partial fraction decomposition. Okay, now notice we do not have a bigger power on top, so we're not going to do the long division. Okay, so what we need to do is factor the denominator, right? So what is x cubed minus x equal to? And we can pull out an x and we get x squared minus 1. And if we pull out, or not pull out, but we can write x squared minus 1 as a difference of squares, right? X minus 1 times x plus 1. So I'm going to do the PFD over here. This means that, or you know what, actually, let me do the full PFD on the other side, okay? So we have x squared plus 2x minus 1. So x squared plus 2x minus 1 over, and then the factoring is x minus 1, x plus 1. So what is this going to equal? Remember, we have one unknown for each linear. So it's a over x plus b over x minus 1 plus c over x plus 1. So we need to multiply now the entire equation by the LCD. In this case, the LCD is x minus 1, x plus 1. When we multiply that, we get x squared plus 2x minus 1 is equal to a times x minus 1, x plus 1, plus b times x plus 1, plus c, x minus 1. This time I'm going to jump right into using the shortcut. Otherwise, this would actually be a 3x3 system. No fun to solve, right? So we can plug in any values we want. So let's plug in stuff that's going to get rid of the right side. First, I want to get rid of the a and the c. I can plug in x equals 1, right? So if I plug in x equals 1, on the left, if I plug in 1, I get 1 plus 2 minus 1. That's just 2. On the right, if I plug in 1, I get 2b. And that gives me b equals 1. Pretty simple there. So what else can I plug in for x? I can plug in x equals 0. And if I plug in a 0 on the left, I get -1. And if I plug in a 0 on the right two terms go away. I'm left with a times -1 times +1. So a times -1. So if I divide both sides by -1, I get a equals 1. And if I plug in x equals -1, if I plug in a -1 on the left, I get -1 squared is 1. I get 1 minus 2 minus 1. So that's -2. What do I get on the right? The only thing I have left is c times -1 times -2. So this means that -2 is equal to 2c, which means that c is equal to -1. All right, so now I go back to my original problem. I know what the partial fraction decomposition is, right? It's going to be 1 over x. So let's write it here. It's 1 over x plus 1 over x minus 1 minus 1 over x plus 1. Before we go ahead and integrate this, I want to point out that you can always use algebra to add these three things up and see if you get back to the original problem, right? You can always check that way. So let's write this down. We got 1 over x plus 1 over x minus 1, and then minus 1 over x plus 1. So what is this equal to? We end up with the natural log of x plus the natural log of x minus 1 minus the natural log of x plus 1, and then plus c. This one was really easy. They were all ln's, and also we didn't have to divide by any slopes because the slopes of all of them are 1 at the bottom, right? We're going to do 2 more examples. These 2 are going to be trickier. Okay, let's move on to example 9. So number 9, we're going to do the integral of x squared minus x plus 6 over x cubed plus 3x dx. Again, we noticed that there is none of the other methods that we've learned apply to this. However, we can factor the denominator, right? So let's go ahead and factor that right now. So what does x cubed plus 3x become? All we can really do is pull out an x, right? We have x times x squared plus 3, and we cannot go any further than that, right? This guy is irreducible. Again, you can never factor a sum of 2 squares. We can only factor a difference of squares. Okay, so let's go ahead and write that down here. What we're actually integrating then is x squared minus x plus 6 over x times x squared plus 3. Now we're going to use partial fraction decomposition to break this apart. We're going to do this on the next page here. So PFD, we have x squared, let me not write this wrong, x squared minus x plus 6 over, and then we have x times x squared plus 3. Okay, So x squared minus x plus 6 over x times x squared plus 3. So let's go ahead and do the partial fraction setup here. This is going to be a over x, right, because it's linear, but this next one is a quadratic, so remember we need two unknowns, bx plus c over x squared plus 3. Now, multiply the whole thing by the lowest common denominator. So I'm going to multiply the whole thing by x times x squared plus 3. And let's see what we get. We actually get x squared minus x plus 6 on the left. And on the right, we get a times x squared plus 3 plus, and then bx plus c times x. Okay, can I plug in anything to make this easier? Unfortunately, we can do it once, but not twice, right? Because there's nothing that we can do to get rid of the a term. However, I can plug in x equals 0, right? That's going to help with the right term going away. So if I plug in x equals 0, on the left I get 6, and on the right I get 3a. And that means that a is 2. So this is good. Unfortunately, doing the rest of this, I am going to have to go ahead and, use the long way here. However, since I have a equals 2, I'm actually going to go ahead and replace this with a 2. And what I need to do now is multiply the right side out. Okay, so I have 2x squared plus 6 plus bx squared plus cx. And then I'm going to combine like terms. So this gives me 2 plus b. This is my x squared. These are my x squared terms. And then I have a c with my x, and then I have a 6 all alone here. And over here I have x squared minus x plus 6. So I just have to equate coefficients, right? And this actually is going to be pretty easy since we already found the a equals 2 term, right? So because there's a 1 right there, and that's next to the x squared, these two things have to be the same. So this means that b plus 2 is 1, which means that b is equal to -1. Next, this -1 right there has to equal c, right? There's actually a 1 here, it's invisible. So this means that c is also -1. Okay, so remember the partial fraction now, what we've learned, take a good look at this, because we just learned what a, b, and c are. So that means if we were to write that out, it looks like this. 2 over x plus, and then we have bx plus c is -1x minus 1 over x squared plus 3. Okay. How are we going to solve this? All right, this integral is not trivial, but we're going to go back here, and I'm going to show you guys what to do. So we have 2 over x plus, so it looks like this. 2 over x plus -1x minus 1 over x squared plus 3 dx. This is what we have. So what I'm going to do now actually is I'm going to break this up. I'm going to break this fraction up into, so it's going to look like this. And what I'm going to actually do is do these 3 integrals separately, okay? So it's going to look like this. The first integral is just going to be 2 over x. And then the second integral is going to be, I pulled the negative out that time. And then the third integral is going to be 1 over x squared plus 3. Okay. Now, let's go ahead and call these, I'm going to call this guy I1. I'm going to call this guy I2. And I'm going to call this guy I3. And we're going to do them one at a time, okay? So, on the next page, so I1 is the integral of, I believe, 2 over x, right? This is our easiest one. This is just going to be 2 natural log of x. What about I2? This one is going to be, we remember we have an x, and then we have x squared plus 3. So look at it carefully, right? If we let u equal the denominator, then du is going to be 2x, and that's going to absorb the top. So I'm going to let u equal x squared plus 3. So that means du is equal to 2x dx, or 1/2 du is equal to x dx. So this ends up being, I can pull the 1/2 out, and so that becomes 1 over u du. And then when I take the antiderivative, it's 1/2 natural log of u, which is the same as 1/2 natural log of x squared plus 3. That's always positive, so I actually don't need the absolute value there. So I found one answer. I found the second answer. The third integral, though, is the toughest one. The third integral is going to be 1 over, let me remember what it was. It was 1 over x squared plus 3. It's not too bad. So we need to use trig substitution. Okay, we're going to let x equal the square root of 3 times tan theta, right? Because we actually had an a squared plus x squared there. If you forgot this method, then you have to go back and review section 7.3 because trig substitution is exactly the method that we're using here. And so dx is equal to square root of 3 secant squared theta d theta. So what do we get here? If you actually plug that in, you end up with 3 tan squared theta plus 3, and then the dx is square root of 3 secant squared theta d theta. What does the bottom become, right? If I pull a 3 out of this denominator, I get tan squared theta plus 1, which is actually secant squared theta. So the secant squared theta, I actually get 3 secant squared theta on the bottom, and so these actually cancel entirely, and also that square root of 3 cancels with a 3, and that gives me a square root of 3 on the bottom. And so actually, my integral just looks like this. So that's easy, right? This just gives me 1 over root 3 times theta. Now I'm not done because I do have to change theta back using the triangle, right? So what does our triangle say? Remember, if x is equal to the square root of 3 tan theta, then this means that tan theta is x over the square root of 3. Here's our x, here's our square root of 3, here's our theta. So this is going to be the square root of x squared plus 3. Sorry, we didn't even need this triangle, right? Because it's just a theta, it's not a trig function here. So what is theta equal to? This means that theta is the arctan of x over root 3. So this is equal to 1 over root 3 arctan of x over root 3. So finally, we add all three of our answers together, right? We've got these three answers. Remember, it's I1 plus I2 plus I3, so our final answer here is 2 ln of the absolute value of x minus 1/2 ln of x squared plus 3 and then minus 1 over root 3 arctan of x over root 3. Is that correct? X over root 3? Yeah. There you go. Plus c. Tricky, right? Okay, let's do another one. This will be our last partial fractions example, okay? So let's look at number 10 here. We're going to do the integral of x squared minus 2x minus 1 over, this time it's already factored for us. How nice they are. So I'm actually going to do partial fractions on the next page. We know we have to do partial fractions. I mean, the fact that the bottom is complicated and factorable tells us all we need to know. Okay? So let me write this on the next page. So the partial fraction decomposition, remember we are doing x squared minus 2x minus 1 over x minus 1 squared times x squared plus 1. And we know this is going to equal, we have to do a over x minus 1 first. And remember, we actually have to repeat it again because we have to do it 1 for each power. And this is our first time we have a square there. And then we have an irreducible quadratic on the right, so we actually have to do cx plus d over x squared plus 1. So then multiply by the LCD. This LCD, of course, is exactly that denominator on the left. So we have x minus 1 squared times x squared plus 1. So if we multiply that out, we get x squared minus 2x minus 1. And this is going to equal a times x minus 1 times x squared plus 1 plus b times x minus 1 x squared plus 1 plus cx plus d times x minus 1 squared. Yikes, it's a good thing we actually can use the shortcut a little bit here. I mean, we can't use it a whole bunch, which is kind of a drag, but we can at least plug in x equals 1 here. If we plug in x equals 1, let's see here. Oh, I actually messed up here. This should not be here for the b. There you go. See, even your teacher makes mistakes sometimes. There you go. Okay, so if we plug in x equals 1, on the left we get 1 minus 2 minus 1, that's negative 2. And on the right, if we plug in a 1, we end up with 2b, which gives us b is negative 1. Unfortunately, that is all we can use the shortcut for, but hey, at least it's something. So I can replace that with a negative 1. So now let's multiply the right side out. The right side is, let's see here, I'm going to multiply this out. This is x cubed minus x squared plus x minus 1, and I'm multiplying that by a. So I end up with ax cubed minus ax squared plus ax minus 1. And then I have minus x squared minus 1. This is not going to be fun, right? We have x squared minus 2x plus 1, and then I'm multiplying that by cx plus d. So we end up with, first let me do the cx terms. I get cx cubed minus 2cx squared plus cx, and let me do the d terms now, plus dx squared minus 2dx plus d. And so we're going to combine like terms. So on the left, remember, we actually have a 0x cubed here, right? And I'm writing the x cubed down because we do have cubes on the right. So here's what we know then. If we go by equating left and right, if I look at just the cube terms, I have a plus c is equal to 0. Those are my cubes. Now if I look at my squares, I have negative a minus 1 minus 2c plus d is equal to 1, right? And these are the square terms. If I look at x, I have a plus c minus 2d is equal to negative 2. And then if I look at my constant term, on the right I have negative 1 minus 1 plus d is equal to negative 1. Okay, we actually can do a few tricks here, okay? So look at this equation. This bottom equation is nice because it actually leaves us with only one variable, right? So we can actually solve for it right away, okay? Let me make sure I didn't make a mistake here. Ooh, I actually made a mistake. This should be an A. So that's right. So I actually have more than one variable down there, so I need to be careful with what I was about to do. It was actually not correct. But what I can do with this equation here, so here are my equations that I get. The top equation actually gives me that A plus C, and I'm going to write this on the next page because I'm going to have to do some work here, okay? So the next page says A plus C equals 0. Then I have negative A minus 2C plus D equals 2. And then I have A plus C minus 2D equals negative 2. And then if I move the positive 1 to the other side, it goes away. So I get negative A plus D equals 0. Okay. So this is what I'm going to do. I see something right away off the top of my head. I see that I can use this equation to get C equal to negative A. And then I can use this equation to get D equal to A. And then I can plug both of these into either of equation 2 or equation 3. So let me use equation 2 right now. So equation 2, if I plug those guys in, remember C is negative A and D is A. So I get what do I get here? I get negative a plus 2a plus a equals 2, which means 2a is 2, so a is 1. So if a is 1, I've actually got them all, don't I? Because now that means that c is negative 1 and d is also 1. Okay, so if I go back to my very beginning here, so let's remember here, a is 1, so that means I have 1 over x minus 1. Next, b, what was b? b is negative 1. Let me write it this way. I have a minus, right? Minus 1 over x minus 1 squared. And then cx plus d, right? So that's negative 1x plus 1. So I'm actually going to do a similar trick as I did last time, right? I'm going to break it up into 3 integrals. I have 1 over x minus 1. And then I have 1 over x minus 1 squared. I'm actually going to write this as x minus 1 to the negative 2. And then my last one, I'm going to break it up into 2 pieces. So I actually have four integrals, and actually none of them are very hard. Okay, so for this first integral, this guy is just going to be the natural log of x minus 1, right? Now for this one, we actually have something to the negative 2. So this is going to be a power rule, isn't it? Right? And so it's going to be to the negative 1 divided by negative 1. So it's going to be plus 1 over x minus 1. Remember, I'm using the linear substitution shortcut, but if that confuses you, just let u equal x minus 1. du equals dx, and then you'll get there. Now this next one, I am going to do a u sub. U is equal to x squared plus 1, and then du is 2x dx, or 1/2 du is equal to x dx. And so that means that I end up with minus 1/2 1 over u du. So it's going to end up being minus 1/2 natural log of x squared plus 1. This is just like in the last example we did, right? What about this fourth integral? We should recognize that. That's something we know. That is arctan, isn't it? Because the derivative of arctan is 1 over 1 plus x squared, right? And we're done. So for our last thing in this section, we are going to learn one more little technique. The book kind of throws it into this section, which I think is kind of weird. But I want to give one last little thing here called rationalizing substitutions. So the entire technique goes like this. If you have a radical in your integral, you can always get rid of it by letting u equal the entire radical. Now, there's a reason why we didn't use this previously with radicals. Usually this makes your problem worse, but this is actually something that you can try if you're desperate and you don't know what else to do. Okay, I would like to do one example just to show you guys what this looks like. So I'm going to do the integral, number 11. I want to do the integral of the square root of x plus 4 all over x dx. This will be our very last example. Now, the problem is, if that were an x squared plus 4, we could try trig substitution, right? But this is just an x plus 4, so trig sub is not going to work. So we're going to try just letting u equal the entire radical. Now, here's what's nice about that. I can just take, what I can do is I can square both sides first. And then I can actually move the 4 to the other side like this. And now I can take the derivative of both sides. So if I do that, I end up with 2u du is equal to dx. So now I know what to replace my dx with, and I know what to replace my x and my radical with. And so let's see what happens to my integral. I end up with a u on top. The bottom is u squared minus 4. And then my dx becomes 2u du. So I end up with 2u squared over u squared minus 4. How would I approach an integral like this? Well, the bottom does factor, doesn't it? And so partial fractions is probably going to help us here. So to do this problem, though, I am going to do the long division first. So partial fraction decomposition. Remember, we have 2u squared over u squared minus 4. So 2u squared divided by u squared minus 4, right? So when I divide this, I end up with a 2. And if I multiply that, I get 2u squared minus 8. And then if I subtract, I get a positive there. So actually, the only thing I end up with is a positive 8, right? So I get 2 plus 8 over u squared minus 4. And so we're going to focus now our effort on this guy, okay? So 8 over, I can factor that, can't I? U minus 2 times u plus 2. And I know that this is going to equal a over u minus 2 plus b over u plus 2. So this is actually going to be a pretty simple partial fraction example, right? The tricky part was the beginning. So if I multiply this by the LCD, I end up with 8 equals a times u plus 2 plus b times u minus 2. And we're going to jump and do our shortcut because the shortcut works. If I do u equals 2, that gives me 8 equals 4a, or a equals 2. And if I plug in u equals negative 2, then that gives me 8 equals negative 4b, or b equals negative 2. This means that this guy actually equals, don't forget the 2 from the long division, right? But we have 2 over u minus 2, and then minus 2 over u plus 2, which looks very easy to integrate to me, right? So we have 2 plus, let's write this down. So we have 2 plus 2 over u minus 2 minus 2 over u plus 2 du. So we can actually integrate this right off the bat, can't we? This is just going to be 2u plus 2 ln of u minus 2 minus 2 ln of u plus 2 plus c. We are not done though. We can't leave our answers with u, so come back to our original substitution, right? U is equal to the square root of x plus 4. So the answer is going to be 2 square root of x plus 4 plus 2 natural log of the square root of x plus 4 minus 2 natural log of absolute value of square root of x plus 4 plus 2 plus c. This was actually a nice example because we got to illustrate two new points, right? One was this guy right here. This is the new thing that we did, which is we let u be the entire radical in the problem. And this will always get rid of the radical, although it won't always make your problem easy after that, but it's worth trying if you are stuck and you can't do anything else. And then, of course, this was a nice because we got to look at what long division does. And remember, when you use long division, it gives you this extra thing that you can integrate separately. Don't forget about that guy. Okay, everybody, that is it for this section. And this is actually our last integration technique that we're learning in the chapter. So in the next section, we're going to be reviewing all the techniques, and I'm going to be giving strategies for when to use each one. It's one thing when you do a section of homework and you're practicing one method over and over, but in the next section, you're going to get to practice all of them at once, and you're going to have to figure out what method to use. Okay? That's it for this video, guys. Thank you so much for watching. I hope it was helpful.